derivative of log for any base, okay, of x. So here's the function. We want to be able to find what the derivative is. I'm going to try to show you through implicit differentiation how you can come up with the derivative, okay, of this particular function. And it's kind of the last one, okay, when you were studying calculus, or when you are studying calculus. It's the end of the road in terms of all the derivatives, you know, so you've come a long way. And now, okay, in your first kind of calculus course that you have, you want to be able to find what this derivative is. Now, I have done the derivative of ln of x. I can put up a link up above there for you. And this one just generalizes it to any base at all. And then, you know, so how much different is it? Okay, so with respect to that ln of x. Now, in this function, you should, of course, know, okay, so if you're going to be taking your base, so within here, so this particular base that you have, that base, of course, has to be between 0 and 1, or it has to be greater than 1. So that's something that you should be aware of, okay? We can't have the base being negative, when we certainly doesn't make much sense for us to have it 0 or 1 either. So that is the restriction on your particular base. And with that, so with this function, we should know that the domain is actually for x which is greater than 0. And it doesn't actually exist for less than 0 or 0, okay, at all. Now, how does this function look like? So if I kind of go back, I'm going to put this up on decimals, okay, within here. So if I do have this function, and I want to be able to, okay, give the actual result, okay, so let me take a look in here. So that is how the function looks like, and now let's just set it, okay, b is equal to 10 for the moment, but we're going to be able to set it at anything we like, you know, so we said between 0, and I guess, you know, we'll put it between 100 or something like that, and obviously we'll avoid 1 there. But within this, so that's how this function looks like. So that's any log function that we would have. And what we want to be able to do is we want to be able to find the derivative, which means the slope at any given point where this function is defined, which is going to be for x greater than equal to 0. For x greater than 0. It's not defined at 0 in there. Okay, so it'll be actually undefined. So coming back to this, you know, how am I going to find what the derivative is? So it turns out that the derivative itself, okay, if you were trying to find what that derivative is, so that derivative of this function is actually equal to this. It is equal to 1 all over ln of b multiplied by 1 over x. That's what the derivative is. Now, the question arises, why? You know, why is this actually the derivative? I mean, sure, I can memorize this, but where does this come from? And so here is the actual proof, okay, that we're going to do. Now, it's not much of a proof. It's not super difficult as long as you're comfortable with implicit differentiation, which is what I use in the proof. You can use others as well. I'm sure you can find it on the net. Now, implicit differentiation was one of the initial videos that I've done for the chapter when you're studying logs. And I'll put up a link kind of up above there, okay, to implicit differentiation if you want to be able to see it. So with the assumption that you're comfortable with implicit differentiation, let's give this a go. So what I'm going to do is now, instead of writing f at x, okay, I'm going to just, you know, refer to f at x just simply as y. So this is going to be y is equal to log of bx. And you know, so there's really no difference for us in here. So we have all the restrictions that are set. So these particular restrictions are in there. And now let's proceed. So the first thing that I'll do is I'm actually going to raise this. And what I mean by raise this, I'm going to take the base, okay, and do the following little trick. So b to the y and then b to the log, okay, of bx. Now, what I'm trying to do here is I'm trying to actually remove the log, okay, from the equation entirely, because that's not what I want to work with. I want to work with something that I already know, something that I already am familiar with in terms of what the derivatives are. Now, if I take this, now I specifically took b because of the fact that my right-hand side, so all of this is going to fall off, and this is just by log properties, okay, that you have, and this is just simply equal to x. Now, if you've forgotten about that log property, I'll put it up above there. You can go back. It's probably going to date you to grade 11, okay, or at some point whenever you had studied it. Okay, so you can take a look at that, and I go through the reason why that's the case. And here in calculus, I'm just assuming, okay, that students kind of recall it. And if they've forgotten, they can always take a look at the link that I provided, okay, and then they can go back to that grade 11 concept. And now, so on the left-hand side, I still have this. Now, this equation, okay, is much easier to work with because I have now b raised to the y is equal to x. And I'm comfortable with taking derivatives of exponents, right? So that's kind of a chapter before, okay, logs, although logs and exponents in calculus are covered more or less at the same time, but typically you'll do the exponent derivatives first. And the derivative, okay, what I'll use is now implicit differentiation, and I'll differentiate the right-hand side and the left-hand side and the right-hand side with respect to x. Okay, so that's what I'm going to do next. Now, differentiating the left-hand side means that I have to know what the derivative of b to the y is. And that is nothing else but just an exponent. Again, I can put up a link up above there if you've forgotten what the derivative of an exponent is. So within here, so if I do this, then I have to take the derivative of all of this. And now the derivative of that is going to be ln, okay, of b multiplied by just b to the y. And because of the fact that I have b to the y, now I have to use implicit differentiation where that y, okay, is going to get differentiated. So dy dx. And this is my left-hand side, all right? So that's what I would have there. And then my right-hand side, well, the derivative of x is easy with respect to x. It's just 1. That's what the derivative is now. And from here, you can see that all of this, okay, that we have right there is going to fall off, right? So that entire thing, okay, if I take it, what's going to happen is I'm going to have my dy dx, which is the derivative, and this is going to be y all over, okay, and now as you can see here, it's going to be ln, okay, of b times by. But hold on a sec. Okay, as you can see here, I hope, by right here, well, that's by, that's just equal to x, right? Okay, so I can substitute this in here, and I can see that my derivative indeed is 1 all over, this is going to be ln b, okay, times x. Or, you know, of course, you can write this as 1 all over ln b multiplied by 1 over x, which is what I've shown you the derivative actually was. So there you have it, okay? So that's how you can find what the derivative is. I used implicit differentiation to do it, but this is actually the derivative with respect to any base that you like, okay? And that's pretty neat. And now, so if I would go back into that Desmos graph that I did for you, so within there, so within here, and we can choose, you know, we chose b is equal to 10, but we can change that as we go along. Now, let's take a look and see if we can plot what that derivative is. I'm going to actually do a line which is going to be tangent, okay, to each of the points. And we're going to try to find, and obviously the tangent line is actually the slope itself. So I'm going to define here a, that's going to be my x value. So a is equal to, let's put it at 1, and we know that it's greater than 0, and then here I'll maybe put it at 100 here. So that's going to be my x value, and then so now any point is going to be a, and this is going to be f at a, and that's going to be plotting my point. Let's maybe change the color here. I'll change it to green so it looks a little bit nicer. And now I can drag this, and this is the point, okay, that we want to be able to find what the slope is at that point. So we know what that point is. In this case, I put it at 2.62, and then I can substitute it and find what that value is in there. So now if I label it, it's going to give us the actual value rounded off. Okay, so that would be the actual point. Now the slope, so that's m, okay, is equal to, so I'm going to put slope as m, kind of going back to, I guess, probably grade 9 or 10 when you were talking about lines. So the y is equal to mx plus b, okay, line. So my slope m is equal to, and so we said this was 1 all over ln, okay, of b, multiplied by 1 over x. Okay, so this is what my slope is. Now, the x itself, okay, we are setting because we want to know what the slope actually is at a particular point, right? So that point is going to be a, because I'm substituting a for x, okay? So I'm going to put that in there. And that gives me the slope at that point. Now, with that slope, I can actually find out my equation of the line. Y is equal to mx plus b. I have a point and I have the slope. With those two items, I can find out what b is, and b is just equal to y. Well, y is just f at a, okay, minus my slope times a, right? That is what we would have in there, okay? So now let's take a look in here, and let's see what it's going to be complaining about, okay, in there. So we have, so our slope is m, and let's take a look in here. Oh, because I used b as my base, and then I redefined my b. Okay, you know, so let's call this, you know, maybe b2, okay, or b at the slope. All right, so that's what I'm going to refer it to. And so there you have it. We can't have two b's. And now with this, so notice y is equal to mx. Well, typically it would be plus b, but this is b, okay, at the slope. And there you go. Okay, now we've plotted on decimals, and now we can move this point, and it automatically changes the slope for us, right? So we can have this. It's pretty neat to be able to have that. Now, I certainly didn't have to actually show you this, the actual plot and the slope, but I wanted to show you that indeed that is the derivative. And now you can graph it on, okay, you can graph your log function, you can now find the tangent line anywhere that you like, all right? And you can obviously copy the code in here, okay, and then post it up for yourself and then play around with it. All right, so thanks for watching, okay, and now you know what the derivative is of a general log function with any base. And of course, the base has to be between 0 and 1 or greater than 1. All right, that's what you would have, okay, within here. And notice I can now change this, changes the graph ever so slightly, okay, with changing the b, but our slope is still there. Thanks for watching. We'll see you in a future video. Happy calculus study. Bye, everybody.